Hello everyone again, and hello everyone on YouTube. So let us continue with our lectures, and now, to make sure we understand how this one is a continuation of the previous one, let us look at the following. So what did we learn last time? What was the focus of the previous lecture? Does anyone want to tell?
Control of systems with constraints.
Yeah, very good. So, learned how to control them, right? But then, I don't know if I mentioned it specifically, but hopefully I did. What was, the big kick at the end was supposed to be, was that, our constraints were, how should I say it? They weren't really exhaustive in terms of what types of constraints we have. So the tools were general, right? So the tools were, didn't rely on specific properties of constraints, except those tools kind of didn't distinguish between constraint preventing us from pushing through the wall and from, the wall pulling on us, preventing us to leave. So, if you have a point contact constraint, in terms of previous lecture formulation, it is a bolted contact. So you cannot really get away from this contact point. You cannot pull, cannot push, cannot do anything. But in real life, this is not what usually happens. A leg can leave the ground just easily. It cannot push through the ground, so right. That is a big distinction. And what we saw previously was a general framework which missed a big detail. And this big detail, once we have it, we'll understand how it impacts our ideas about control. And the impact will be significant, but it will go naturally into what we discussed previously. So how should I say it? It is not going to be a rewrite of what we saw previously, but this lecture will inform us where we should go next. So it is critically important to understand it, to actually be able to work with systems with constant contacts, with constraints. But at the same time, it doesn't cross out any of your previous knowledge. It's just the fundamental for the next step. So that's what I want you to see it as. All right. Now, let us go into a little bit of what, how should I say it, what we concretely talk about. So let us consider this robot. It's Spot Mini, one of the most popular quadrupeds out there currently. So can you really describe contact points of this robot with this equation? Do you think you can do it? Like, describe it accurately? Well, answer is no, because what does this equation says? It says that some quantity is being preserved throughout the whole motion of the robot's body. So no matter what the robot does, this quantity is going to be equal to 0 continuously. It doesn't matter if, by the way, it is equal to 0 or some other constant. You could always say, equal to 2 or equal to, a vector of quantities is okay. But it means that some quantity is being preserved. That is the main point. And which quantity? Well, the position of those legs, that is what G of Q will be, most likely, right? So the position of those legs, but they are not preserved. They're preserved while they stay on the ground. As soon as they leave the ground, they're no longer preserved. And, if you think about it, what will happen is actually once they leave the ground, they are no longer constraints. So the total number of constraints will change from being, let's say, 4 contact points, each representing at least 3 constraints, quite possibly 6, to, for example, from 4 contact points to 3 contact points, maybe to 2 contact points, depending on how aggressively spot moves. If it jumps, it can go even to 0 contact points. So the number of constraints will change. But that is not the point that I'm trying to make. The point that I'm trying to make is, even while contact does not change, even during a single contact scenario where you have, like, as on this picture, 4 contact points, quite possibly representing 6 constraints each, depending on how you define your, model your contacts, etc. You still have the possibility of any single one of those legs to do this. Oh, sorry, to do this. Okay. Lift up. Okay, can go up, and that is fair. It doesn't, that is possible. In other words, this idea here is, just strange. Like, it doesn't describe what actually happens. Okay. So, good. Now, this is, interesting. Now we need to find out what is going on exactly. Well, here, let us consider this slide. So this is pulled from a paper, this one. And they distinguish those 3 typical models of contact. And when they say contact, they don't mean like bolted to the ground stuff, as we described before, but actual contact. So when you touch a surface, okay, when you touch something. So that's what they mean, contact. What are those models? Well, first is this one. This is contact without friction. So you, by the way, can you see the errors, or do they disappear for you? Can you currently see 2 arrows? I mean, I'm just checking. Like, let me know if, for some of you, the arrows on the screen disappear. Zoom sometimes have annotation glitches, and then don't want you to, have trouble. But anyway, so you have this first contact. This first contact has no friction. So it means that it can provide force only in the normal direction to the surface. So this is the surface, and your contact can only provide more forces that are normal, so perpendicular to the surface. Okay.
Sorry, I have a question. If you have some make some annotations on the screen, we don't see it. So we see only presentation, clear
Really?
presentation. Yeah, without any handmade writing.
Oh, really? Good thing that I asked. So, like, right now, for example, you don't see what I drew.
Mm-hmm.
Oh, okay. What should I do? What should I do? What should I do? What should I do? Just checking. What about now? Can you see something?
No.
Okay, let me try to do this. So can you see if I draw the here? Did you see me drawing?
No, we only see the pen, but drawing.
Okay. I understand. All right. Well, it's unfortunate. It's definitely unfortunate. All right. I will try to continue the lecture without referencing anything that I annotate. I apologize for, but no. Okay. So I will try to not reference anything using annotation. I'll try to say like left, right, etc. Okay. So thank you so much. It was very helpful. Good. All right. So the figure 2, the A, this thing. Okay. Let me use mouse. So figure 2A is there's no friction contact. So as I said, the only forces possible go into the normal direction. Okay, good. Now let's go to the next one. Next one is figure 2B, this one. So here we have friction and normal reaction force. But notice that you have this cone. What does it mean? Well, it means kind of refers to the fact that friction cannot be arbitrary. Let me put it this way. Imagine that you, have a brick on the ground, just brick sitting on the ground. Okay. You try to push it with your finger. Okay. You can expect a reasonable amount of resistance. So if you push it slightly, it's not going to move, right? That's what we describe as friction. Like the force that actually prevents your finger from moving the brick is friction force, right? Okay. Now, imagine now that you have a piece of, like empty carton box, empty cardboard box, right? Paper box or whatever. It's very light. You can push it with your finger and you can expect that it will move even from a very small force, even from a very small push. Why? Oh, it weighs less and you expect the friction to give in, so to saturate and stop preventing the motion faster. So friction is somehow related to the amount of weight the object has. And from high school, you probably remember the ratio that's described as friction coefficient, right? So when we talk about this ratio, it's convenient to talk about this, about this cone that you see on the picture. This cone kind of represents that, if you have high, you can think about this way. Vertical direction of the cone is normal reaction. Horizontal direction of the cone is friction. So at the very bottom of this cone, the normal reaction force is almost zero, okay? And, if you have such a low normal reaction force, you cannot expect to have a big friction. Your friction is also almost zero. At the top of the cone, you have a significantly large reaction force, so you can expect a reasonable amount of friction. Friction here you can see is still less than reaction force. Reaction force is a tall vector. Friction is going to be very short vector because the cone has this like very narrow shape, right? If it was like a very blunt angle, then it would be you could have bigger friction. Okay, good. But here is the thing. In real life, friction is actually usually lower or equal to reaction force. So a cone, this sharp cone is a good description. Actually, the angle of the cone that you can see on the figure as arctangents of mu, this thing is, this angle is arctangents of the friction coefficient. So that's the physical interpretation. Okay. Let us, that is pretty much what I want to discuss here, because I ended up discussing it on the previous slide. I apologize. So friction cone is exactly that. So you can imagine your manipulator goes to touch a wall, right? And what happens is you have a friction cone that is perpendicular to the wall. Notice that on this figure, your your friction cone is not perpendicular to the link. It is perpendicular or parallel or anything. It is perpendicular to the wall, and that is how it is. Why? Because friction cone describes the relations between normal reaction force and friction force. Normal reaction force is normal, so perpendicular. Friction is tangential, so it is tangential force means it is in this tangential direction, right? It's a direction along the wall. Good. Now, let us try to discuss it. So this is going to be a little bit difficult without annotation now, but hopefully you can follow me through the slide. So we have this Fn vector. You can see it at the beginning of the text on the slide. And this Fn vector is a normal component of the reaction force, okay, or normal reaction as we call it. So this is the component that is perpendicular to the wall. Then you have F friction. That is the tangential component of the reaction force. Okay. So I'm almost tempted to restart the call just to have annotations, but we'll try for a little bit longer before we do drastic measures. Okay, so and you have this F friction, which is a tangential component. Okay, so then you can have this expression number 1. What does it say? It says that norm of friction is less than norm of the normal force, normal reaction force, times the friction coefficient. Okay. So this is something that you should have remembered from school. Do you remember it from school? What do you say? Did any of you saw this stuff in school or in theoretical mechanics or somewhere else? Really? No one remembers? I mean, okay, maybe not this form, but you probably saw that friction force is maximum value of friction force is normal reaction force as a scalar times friction coefficient. Okay, anyway, if you didn't see it, that's good now. You see it now, so it's okay. Good. Now notice, please, that in expression number 1, you have you have vectors. So you have vectors, and they represent, we take norms of those vectors. So here, Fn and F friction are both 3-dimensional vectors. Okay, that is important. Okay, good. Now, let us note that this expression on top of the slide does not describe friction cone. A friction norm is less than mu times norm of normal reaction force. This does not describe a friction cone, nor does it represent actual realistic contact. Okay, why? Well, there is a good reason. The reason is it doesn't force reaction force to be positive, so to be to push us instead of pulling us. Reaction force, normal reaction force, cannot pull us in a unilateral contact. And by the way, what we talk about here, all of it is called unilateral contacts. So contacts that can prevent you from penetrating the surface, but don't prevent you from leaving the surface. Okay. So this expression is not enough. So we can actually try to fix it. How do we fix it? Well, we first add a unit vector n, which you can see in the second paragraph on the slide, a bold letter n. This is a unit vector that goes, is normal to the contact surface. Okay. And we can complement it with two vectors which are tangential to the contact surface, tau1, tau2. You can see them 2 lines below. Those two are, those two are also unit vectors, and together with n, they form basis, a orthonormal basis in the three-dimensional space. So every vector can be expressed in terms of this basis. Okay. Now you can define your total reaction force as F bold on the bottom of the slide. And what you can do next is you can find your normal reaction force as a projection onto the vector n. So basically, the way you do it is, as you see on the bottom of the slide, you find a dot product, or n transpose f. This is dot product between n and f, right? And then you multiply it by n to retrieve the directionality. So dot product will give you a coordinate. Then you multiply it back by n, and you get a vector in the original space, and this vector will be Fn. If you look at it carefully, if you open the brackets, which are completely unnecessary for this expression, and I mean, they're unnecessary in a sense because inside there is a scalar, and you cannot, for example, rearrange the terms here, etc. But long story short, this expression is very similar to a projector. Since n is a normalized vector, it doesn't make f scale. So this transpose is slightly similar to pseudo inverse, and this whole thing kind of is very similar to a projector onto n. And that's pretty much its purpose. So we could have defined the projector onto n, onto vector n, and it would have been pretty much the same. So that's it. All right. Now for tau, you can last expression on the slide is big T is equal to tau1, tau2. So this is like two unit vectors put together to form a basis, some sort of a basis in the subspace, in the tangential subspace. And you can project F onto T exactly the same way. You can see the expression on the left bottom part of the slide. F friction equal to T, in the brackets T transpose F. That is the same thing. You pretty much want to first project F onto T by multiplying it by transpose. You get coordinates in terms of basis T. Then you multiply those coordinates on the basis T to get a vector in the original space. In other words, if you open the brackets and you recognize that T transpose and T inverse are one and the same here, you would see that this is just a projector onto a column space of T. So sorry for algebra maybe making it less clear, but what we do is we just represent those two vectors, F friction and F normal, in terms of those unit vectors n and tau, multiplying one important vector F. So now we have just F and those vectors tau and n are constant, okay? F is not constant. So here we have like a representation in terms of like one vector F and a bunch of constants. Good. So like where previously we had two vectors Fn and F tau, F the direction. Good. Now let's see where it leads us. Well, it leads us to this expression, expression number 2. Notice what we have here. What we have here is very interesting. So first of all, we have this two projections. So it is exactly the same as previously. On the left-hand side of this expression, what we have is a projector of F onto this vector T, okay? On the right-hand side, we have a projector of vector F onto this vector N. But now notice something strange happens. We don't project back onto, we miss the second part where we, on the left-hand side, we previously, let me go back. Notice on the bottom of the slide, what we had is all our expressions were of the form F, T times open brackets, T transpose F, N times open brackets, N transpose F. You see it, right? Now we don't have it. Now we have just stuff in the brackets, basically. Why? Well, why did we have this, N times open brackets, N transpose F? Well, N transpose F gave us coordinates in this new basis. Multiplying it by N again on the left gave us a representation not in terms of those coordinates, but in terms of the original space, okay? Three-dimensional space. Like N transpose F is a one-dimensional coordinate. Multiplying by N again gives us a three-dimensional vector. That's what we use in comparison. But here's the thing. When we take a norm of a three-dimensional vector, we don't have to, the fact that it was multiplied by unit vector doesn't actually change the norm. So instead, we don't have to have the scalar multiplying a unit vector. You can just take scalar. That's why we have N transpose F. The same here on the left-hand side. We don't have to have a scalar, two scalars multiplying tau1 and tau2. We can just as well keep those two scalars. So F, so tau1, tau2 transpose F, that is a two-dimensional vector. We can just as well take a norm of this guy. That's like what we have, expression 2. I hope it is at least a little bit clear. Is it? Any questions? I think maybe like the explanation is not perfect, and we should have maybe written it in terms of scalar examples. Maybe. On the other hand, if you think about it, I promise you it will make perfect sense for you. Okay, no questions so far. Good. So now, how does this help? Well, there is one big way in which it helps. Look at the right-hand side of the expression number 2. This is dot product, okay? Can be positive. Oh, yes, right? But when? When will it be positive? Mu is basically always positive. So when is this dot product N1 N transpose F is going to be positive? Any answer?
It depends on angle of dot product. So between 90 and 0, it will be positive result.
So in other words, when the vectors N and F point in the roughly the same direction. So they are, how should I say it? Yeah, probably cannot give a more precise definition than you did without, repeating my original question. But anyway, when they roughly point in the same direction, right, then the dot product is positive. When they roughly point in the opposite direction, the dot product is negative. When they are perpendicular, the dot product is 0. That's like very imprecise, but
Yes.
Yeah, but you understand the point, right? Okay, good. That's pretty much what you said. Good. Now, if the point in the opposite, here's a wall, and here's the normal direction to the wall. Okay, like in this dimension. Okay, this is where normal vector points. If your force, total force, points kind of this way, maybe this way or this way, this way, or even like this way, the dot product between normal vector and this force will be negative because they point into different half planes, basically. Like if your normal vector, kind of defines the half space, they will point into different half spaces. So that will be negative. Okay. Good. Now, please notice the left-hand side of this expression. The left-hand side of this expression, number 2, is a norm. Can norm be negative? Someone tell me?
No.
No, exactly. So in other words, this inequality will hold, and norm has to be less than or equal to some value only when this value is positive or 0. If the right-hand side of this inequality is negative, this inequality will never hold. Okay, makes sense, right? So this is how we tricked this whole system into never producing forces which point into the wrong direction, so which pull on us. Because if the force that wants to pull would have to point into this direction, right? Here's the wall, it will have to point into this direction, whereas this is a norm. So it will produce a negative right-hand side to this inequality, and inequality will never hold. So if we require this inequality to hold, this inequality covers this part as well. You cannot possibly produce forces that pull on us. Okay, that is why we went through this nonsense with with coordinate representations, because here we don't have to, we already cover this special case. So we don't only cover the friction force being limited, but also we cover the fact that normal reaction force can only be point along the, should be co-directional with the normal unit vector. Like normal reaction force has to be co-directional. It cannot point into the opposite direction. Good. Now, let us consider this. So this is the same expression, it's called number 3, but it is the same expression as number 2. So this, notice, assumes that your decision variable, so the variable that can, decide if the equation is false or true, if it holds or not holds, is F. Okay. So force F. This is a good choice. As we just saw, it allowed us to describe friction cone. But that is not the only possible choice. So A different choice is expression number 4. Notice it has 3 lines. And in those 3 lines, it describes exactly the same thing as expression number 3. So first line, well, it is a scalar representation of the expression number 3. Here you just say that T1 is what you need to multiply tau1 with to get the first component of friction. T2 is a coefficient that you multiply tau2 to get the second component of friction. Notice the second line. That's exactly what it says. That is the definition of T1 and T2. And so those are coordinates that you get after, in the original expression, multiplying, tau1, tau2 transposed times f. That is, the answer to this is T1, T2. Okay. So norm of T1 and T2 is square root of T1 squared plus T2 squared, by definition of the norm. So here. Okay. Now this expression is should be less than or equal to mu times n, where n, a scalar n, not a vector n, is is a coefficient that you multiply by unit vector n to get normal reaction force. That is the third line in this expression. This expression 4. Does it make sense? Does the expressions 4 make sense too? Ask any questions if you have them. Notice that we here our parameters or our decision variables are T1, T2, and like scalar n. What does it give us? Well, original f can be expressed in any coordinate system. We can choose to express it in in any basis that we want, and that gives us more freedom. But also we need to make the choice. So same, but in this choice we'll have to inform in which coordinate systems n and tau1, tau2 are expressed. By the way, if you find n, tau1 and tau2 can be found as null space of a basis of n. So okay, so good. But the expression number 4 actually dictates us all of this. They just say, not all of this, but we choose in which basis we represent n unit vector, tau1 and tau2, and from this we automatically get representation for f. Instead of talking about f as a vector, we just talk about scalars, T1, T2, and small n. So our decision variables are still 3, but then our scalars is pretty much exactly the same thing, just a little bit smaller. That's all. Okay. Now, by the way, do you have questions? Let me pause a little bit. Please make sure you understand everything that we just said.
So I have a question. The fourth equation, the system of 3 equations, as I understand, these parameters, T1 and T2 and n, it's give us opportunity to work on this friction friction cone. So it's like for example, make it more narrow or make it more spare. So as I understand, or it's only for representing. So I don't really understand this part.
Okay, so friction cone entirely depends on mu. Mu is the only thing that describes friction cone. If mu is small, then friction cone is narrow. If mu is big, friction cone is wide. That's all. Because mu is equal to wait a second, let me not make any mistake. Arctangents of mu is the angle of the friction cone. So, but the expressions themselves are just, 3 and 4 are exactly the same, except in 3, we parameterize our reaction force using F, which is just a vector, total reaction force vector. And we say that this vector should be such that if the norm of it times T transposed should be less than mu times N transposed F. So it just has to have those conic constraints.
Conic constraints. Okay.
Yeah. Whereas in expression number 4, those same constraints become constraints on T1, T2, and N. So you say square root of T1, T2 should be less than mu times N. And then you can retrieve the friction force and normal force from the second 2 lines in the expression number 4. But but those retrievals are just if you need to use them. If you don't want to use those things, you can just leave them be. So, okay.
Okay. Yeah. Now I see.
Also, this is not written here, and this is a mistake. But the expression number 4 should also have additional line where it says that n is strictly positive, because here n is defined as a coefficient in front of unit vector n. So the scalar n should be strictly positive. That is important because otherwise it can actually produce pulling force. So, okay, good. No more questions? Anyone wants to ask? Okay, well, I assume that it's it. By the way, like today we are, going fast, and don't feel bad about asking questions. Though I'm saying we are going fast, but we only have half an hour left. So maybe we are not going fast. Maybe I'm just not looking at the time. So anyway, let us consider this. So assume we have a single contact point, K, at the top of the slide, at which the contact takes place. So this contact should take, as long as it holds, should take away 3 degrees of freedom from your robot. Of course, assuming that your robot had those degrees of freedom to give, right? If it is a planar robot, it won't have one of those. But anyway, it takes away 3 degrees of freedom from your robot. And it does it as expression number 5. Notice the right-hand side is not 0, and that is okay. We can always put those expressions from the right to the left, right, with the minus sign. That's okay. Now, what does this give you? Well, it gives you an expression for Q as a variable, which have to hold. We saw it plenty of times before. That is just a constraint. So 3 constraints for 1 contact point. Sounds good, right? Okay. Now assume that you don't have friction force. So you have a contact point, and you have a normal vector n. You can see it in the second line, in the second paragraph. Normal direction n. Then, you can only take away 1 degree of freedom, because the contact point is free to slide across the surface, but cannot penetrate the surface. Okay. So it, 1 degree of freedom, this degree of freedom, is lost, but those 2 are, still here. So how do we express it? Well, as expression number 6. So as n transpose rk, where r sub k is the where r sub k is the position of the point k, radius vector, as we call it in Russian textbooks. So n transpose rk is basically a coordinate of rk on the vector n. This should remain constant. Okay. But you know, I chose to write it as equal to g of k of q. Why? Well, imagine if your surface is actually not a wall, but something like this, like what I draw here with my hand. So your, your contact point cannot penetrate, but can move along the point, the surface, right? Can move kind of like this. So then, imagine that this is your robot, okay? Then, depending on the configuration of your robot, your position in the normal direction is described, being here or being here or being here or being here. It's like normal direction changes, and with which changes the how much you can sort of move along this normal direction. So here n should also be a function of q. But for a wall, for example, it would be just 0. Oh, sorry, like some zero value, or not necessarily 0, but some constant. So expression number 6 would have a constant on the right-hand side in the case of a straight wall. Okay, so just notice this is a scalar equation. So expression number 6 is scalar. Good. Now, imagine instead of a point, you have a whole body coming into contact. Imagine your foot, or a foot of a walking robot. That is the whole body, and it directly contacts the ground. So this whole body will lose 6 degrees of freedom. So all degrees of freedom that it has, if it contacts the ground, can lose at least 6 degrees of freedom. Doesn't have to, right? But it can. So if you completely place your foot on the ground, that's what you're going to lose, 6 degrees of freedom. If you only contact the ground with the edge of your foot, you can still like rotate your foot, for example, right? Or if your ground is slippery, your foot can still slide it. Apologies. Your foot can still slide relative to the ground. So then you're not going to lose 6 degrees of freedom. But if your foot is firmly placed on the ground, you're going to lose 6 degrees of freedom. Okay, and that is what I've written in expression number 7. That is your foot losing, or the body losing translational degrees of freedom. That is the first row. And then it loses rotational degrees of freedom. That is the second row. Okay. So second row represents Euler angles, and they encode rotation. And I say that they're constant now. Good. Now, assume you have many contact points, more than 3. And they're not lying in the same line, all of them. This kind of tells you that if the body has more than 3 contact points, or at least 3, not lying in the same line, it is static. That is something you should have studied in theoretical mechanics, but you can also think about it this way. If you have a chair with 3 legs standing on the ground, you can expect the chair to be stationary, right? So That's enough to fix the chair on the ground. 3 points. 1 point, you can still move around, in many ways. 2 points, you can only move in like one way on the ground, and 3 points, impossible to move anywhere. So good. So you can make the body static, just defining expression number. Defining expression number 8. Okay. So just expression number 8 will define the body to be static. You don't have to go into Euler angles for that. You can just define those triplets that I showed you here, and define at least 3 points which are not collinear, and that's it. You are getting your static equilibrium described through those contact points. Okay. But notice that there are some details. First detail: if you if you introduce more than 3 points, like 4 points and more, they don't actually change the fact that the body is static, right? 3 points on the ground, or 4 points, or 5 points on the ground. You saw tables, chairs, etc. Doesn't matter how many legs they have, 3, 4, or 5. They're still stable. Actually, we can talk about tables with 4 legs being less stable, but that's because of uneven ground, because they don't actually have a contact with all 4 legs. When they have contact with all 4 legs with the ground, they're stable, same as 3-legged tables. Okay. Now, number of points will make a difference if you have a friction cone. Why? Oh, because let's say you have 2 points here. Okay, I'm trying to show, 2 fingers. I'm trying to show. You have 2 points here and 1 point all the way here. Okay, so 2 points here, 1 point of contact all the way here. And then imagine you have a force that pushes at your body here. So here, the friction force can be violated very easily. Whereas here, they would not experience, they would just experience somewhat like rotational things. But this guy will take the blunt of this force. Now imagine instead of 1 point here, you have multiple points here. I don't know. How should I say it? How should I put it? I'm not sure if I'm giving a convincing example. Maybe not. Because if you have more contact points, reaction force will go down, right? So maybe there wouldn't be much of a difference in terms of how many contact points you have in this particular one. But there would be, I guess what I wanted to say was there would be a difference for the algorithm, because you would have 3 friction cones to check, not just 1. And the number of decision variables will increase. Each friction cone has 3 decision variables. If you have just 3 friction cones, it is 9 variables. But if you have 5, you have 15 variables, and whereas for 9 variables you couldn't find a solution, maybe for 15 you would find. But this section, I'm slightly hesitant to give anything definitive. I'm not sure. I didn't do the math myself, so I don't know if it will actually make a difference in terms of the existence of solutions. If I can find an example of where additional contact point without a mass redistribution would actually make the solution more feasible. But it kind of sounds like it should be. Yeah, it sounds like it should make a difference. I mean, the way you can think about it is as such. Imagine you stay on 2 feet on the ground and someone pushes you. If you can put your hand on the on the wall, you are much more stable, right? Compared to if you just stay on your two legs. So mass distribution is the same, but extra contact point makes a big difference. That's I guess would be a good example. Okay, good. Now, also different choice of contact points will lead to different constraints expressions, different Jacobians, and different Cartesian reaction forces. So what you get out of your mathematics will be different depending on what exactly you choose as your contact points. So, and often enough, when you describe robots, you would have a choice. Describe it with like 3 points, 4 points of contact, 5, 10, 20. This makes a difference, and you should realize that it also makes a difference in such objective things as Cartesian reaction forces. You would think that those things you can measure, so they are uniquely defined, but no, actually they're usually distributed. Your contact is usually not a point contact, but a distributed contact. So a contact through a surface, not a point. And this means that your idea, or for example, your foot has a, exhibits pressure on the surface, not on the point. Okay, so you have a distribution of forces, some vector field. So you would have to basically, just assume you have like 5 contact points, or 3 or 4. And this assumption will lead to different answers. So that's important to think about. Next, let me just show you one strange example. That one I think is important to see, but it isn't, we are not going to have something like this in practice, but just to show you. So there was one, on the picture originally, let me just go all the way back. On this picture, we had section C. So figure 2, part C. Notice they say it is a soft finger contact. That is, it is a contact that prevents you from doing this kind of stuff. Let me show you, from doing this kind of stuff. You cannot really rotate around the axis. You have enough friction. So this makes sense, right? Put your brick on the ground and it's not going to rotate along the ground. Except brick is the body, not the point, but you get the idea. Okay, good. Okay, good. Now, how can we describe it? Well, we can describe it as I put in the expression number 9. You have still 3 position constraints, and now one extra, which is a constraint on the angular velocity, omega. Okay? Angular velocity constraint, omega. This it requires that omega projection onto normal direction is 0, which would means that it cannot rotate along this direction. The body cannot rotate along this direction. This is a 4 degree of freedom contact, so it takes away 4 degrees of freedom. Now, does it feel strange to you? This expression that requires you to, as it prevents velocity from changing. It doesn't have anything to do with positions. It only prevents the velocity from happening. Does it feel strange? Well, hope it does, because, originally, how should I say it? We've always talked about positions, angles, but not about velocities. But here we suddenly start to talk about velocities. Well, how should I say it? I don't know if I'm going to be able to demonstrate it very effectively. I will try. But so imagine this thing. So it cannot rotate around the axis pointing into this direction. Okay, so it cannot rotate around. Let me write something here. cannot rotate around this axis that is written as a dot. Okay. So well, this is illegal. Okay. Good. But other two rotations are legal. Well, notice that this line with the also springs is vertical now. So since this rotation is illegal, you would assume that this orientation would also be illegal, right? You cannot go from this orientation to this orientation, right? Or from this orientation to this orientation. Those are illegal, right? Well, I claim it is not true. Why? Well, first of all, I will rotate it this way. Notice the axis now points up, right? Now I cannot rotate it around this axis any longer, right? Because the axis, illegal axis, points up. Now, so again, I rotate it this way, right? Now I'll rotate it this way. So illegal axis points into this direction now. You can see this axis points into this direction. So I cannot do this, but this is perfectly legal. So now I will rotate it this way. This was illegal again. Axis was pointing in this direction. So now you can see I obtained a new orientation, which was illegal, because this was illegal. But I obtained it in a legal fashion. I didn't do anything wrong. This represents the fact that for rotations, just defining an axis along which you cannot rotate does not prevent you from achieving the same orientation by different rotations. That is how rotations work. They're a little bit strange. So for this type of axis, for this type of problem, you have to have a constraint on velocities, not on position. In the same way, you can think about the skater problem. Like the skater cannot move sideways, right? It can only move up and down, okay? But it can move, so let's say I put it somewhere here. It cannot move here, right? It can only move up and down. But I can move it up, then back, and it would arrive here. If you ever, skated, you know that you can arrive at any position on the skating board, skating field, but you cannot move sideways. So, but you arrive anywhere. You just arrive using direct motion, maybe backward motion, stuff like this. So that is another example. So this is what they call non-holonomic constraints. And this is why, because you cannot integrate it to achieve expression in terms of Q. You can only have expression in terms of Q dot and Q. This will break our reasoning that we had previously. So this type of constraint cannot be directly used in our previous formulations. Okay, you would have to, we also call it kinematic constraint, and you would have to just rewrite everything we did before to accommodate this guy. For example, you would have to only differentiate it once to achieve your desired differential algebraic equation form. Okay. So just heads up, some constraints are different from the others, but we're not going to encounter those in our practice here in this course at least. But now you saw non-holonomic constraints. And in robotics application, this is the soft finger contact that the writers pointed out. Okay, good. Now, just a few words about violating friction contact. So, we said that friction cone exists, but does it always hold? No, of course not, right? You can push the brick and it will start to slide. So friction cone is violated. So as soon as N transpose F you can see it on the first bullet point, but also n transpose F, as long as it becomes negative, that means the contact is disengaged. So you left the contact point. It's not going to pull on you. The contact just disappeared. So every other aspects of the contact, friction force, etc., are going to disappear as well. So good. If the force required to maintain contact is outside of the friction cone, but this quantity n transpose F is still positive, this means that you are no longer in the static friction, and instead the contact point is going to slide. Okay, it's going to start to move. Okay. You can model this as the first contact that we described, contact without static friction. So, you still have the normal reaction force, which prevents you from penetrating, but you can now move along the surface. Okay. Now, even though you don't have static friction, you can have a friction force, like sliding friction force, which is often modeled as being equal to normal reaction force times friction coefficient, maybe different one, but friction coefficient times the direction of the velocity with a negative sign. Why? Because if you move this way, you can expect the friction force to try to prevent you. So it will move, it takes the direction of the motion here, opposite sign, and that's where your friction force points. Okay, so that is how you model sliding friction. We're not going to go into this here too much. It is interesting, but it is also fairly simple. So that's how you can model friction. Actually, this is the direction where you go into tribology. Tribology is like a science for friction forces. At least that's a Russian name. I'm not sure if it is the correct English name. Tribology. It describes how materials interact through friction. And while we have approximate models that work very well for some applications, it is people who spend their whole life on it still say that their model for friction cannot predict even very basic contact interaction scenarios. So be aware of science currently not being able to have exact models of friction. So don't rely on the approximate models. You can use them whole day. Exact models, not really, especially for sliding friction. Static friction doesn't require models. It just requires, it does require models, but the model kind of goes into when static friction becomes a sliding friction. So into, what do they call it? Friction cone. Okay. I recommend you to read this book. Sorry, not book, web page. It's actually a very, very small web page, but just to brush off on the terminology and understand how top researchers in the area of uses. And that's it. No homework today, but the homework that you have been doing, please submit it this week. I will remind you on Thursday, and by the end of the week, I hope you will submit your results. Okay. Do you have questions about the material? Okay, if not, I will stop the recording.